Good morning, dear friends. Today again we have assembled so as to have an expert lecture on combustion of fuels, and this is again along the series of the Facebook live session. Now, as we are familiar, you are staying at home and I am teaching from here. So it's a mode of connectivity between you and me, and we are trying to get in connection so as to the teaching learning process can be carried out easily. Now today's session we will be actually discussing about fuels, the combustion of fuels. So now the process of combustion. We all are familiar with the process of combustion, and combustion is actually a process in which actually burning takes place, and it is actually the oxidation. For example, carbon plus O2 gives carbon dioxide and water, and at the same time heat is released. So it is an example of exothermic reaction. So you can see that carbon combines with oxygen to give carbon dioxide plus water, and it is actually the complete oxidation. The process involving the combination with oxygen. Had it been an incomplete oxidation, then the equation will be represented as carbon monoxide. This carbon monoxide then further combines with oxygen. So this is actually the partial oxidation. Now the main thing is that it is the carbon which combines with oxygen results in the formation of carbon dioxide and water. Carbon dioxide and water, and heat is actually released. So what is happening is carbon plus half O2 gives carbon monoxide, and half O2 again combines, it results in the formation of carbon dioxide, the entire process. Now when we speak of any fuel, the fuel actually consists of carbon and other elements are also present. When you consider an organic fuel, carbon, hydrogen, nitrogen, oxygen, sulfur, etc. substances are actually present in this fuel. If the fuel consists of only carbon and hydrogen, it is called as hydrocarbon. Example, the simplest hydrocarbon, methane. So methane combines with oxygen and will result in the formation of carbon dioxide and water. If you try to balance the equation, it comes out to be like this, plus heat is given out. So this is actually the process of combustion of methane. It results in the formation of heat. Now say if you are having a molecule like C4H10, butane, then how to balance the equation. So we will learn how to balance the equation of hydrocarbon when it combines with oxygen. Let us, for example, consider a hydrocarbon as CHHY. For example, it can be C4H8, C4H10, etc. Any hydrocarbon that can be actually present. So we are trying to find out how to balance the equation. Now see, carbon individually, if we try to balance, it gives Cu2. So therefore, if you are having X atoms of carbon, it combines with X atoms of oxygen and results in the formation of X molecules of carbon dioxide. Similarly, hydrogen combines with oxygen and results in the formation of water. Now see, if I convert it like this, half of hydrogen molecule, it will be 1 by 4 molecule of oxygen to give 1 by H2O. This is for one atom of hydrogen. Therefore, if according to the hydrocarbon you are using Y atoms of hydrogen, it comes out to be Y by 2 hydrogen plus Y by 4 of oxygen will give you Y by 2 moles of water. This is the second equation. So adding equation 1 and equation 2, that is adding this equation and this equation, we can write as X atom of carbon plus Y by 2 atoms of hydrogen combines with X atoms of oxygen plus Y by 4 atoms of oxygen to give X molecule of carbon dioxide plus Y by 2 molecule of water. Collectively, it can be written as this is nothing but CXHY combines with X plus Y by 4 of oxygen to give X atoms of carbon dioxide plus Y by 2 atoms of water. So you can see that, so what we have seen that when you are using an hydrocarbon equation like this and you want to combine with oxygen, you have to use the stoichiometric relation as X, where X is number of atoms of carbon, Y by 4, where Y is number of atom of hydrogen present in that hydrocarbon, whether saturated, unsaturated, cyclic, aromatic, whatever, combined with oxygen, it gives. Now let us apply the same thing to this C4H10. So you can see that C4H10 plus X means 4 plus Y by 4, that is 10 by 4 of oxygen will give you 4 times of carbon dioxide and 10 by 2 times of water. So it will be written as C4H10 plus 26 by 4 O2 gives 4 CO2 plus 5 H2O. It can be seen that 36, so 4 to the 8, and then in this manner actually the balance equation can be obtained of this particular thing using this particular equation. So the atom of oxygen, the atom of hydrogen, atom of the molecule of carbon dioxide, the molecule of water, etc. can be obtained by this simple stoichiometric relation. Now, while using or dealing with, there are certain principles of combustion. There are certain principles of combustion. Combustion is actually a process of oxidation, and what we have to consider is complete oxidation. We have to consider complete oxidation. It is when we burn in air, then air, it is a mixture of gases. Air is a mixture of gases, and the most important thing is that the major contributory gases present in it are oxygen and nitrogen. Nitrogen do not contribute to combustion. It creates an inert atmosphere. If nitrogen was not present in the atmosphere, everything could have burnt and resulted into carbon dioxide. So it produces or provides an inert atmosphere. Now, when you compare them, then the comparison is by volume and by mass. There are two things, that is by volume as well as by mass. When by volume, oxygen is 21% by volume of air, and by mass, oxygen is 23% by mass of air. So important thing is that oxygen is 21% by volume of air, oxygen is 23% by mass of air. Other gases are also present, but they are present in traces. So what is done is, now nitrogen, it is assumed that nitrogen will be about 79% by volume, and nitrogen is about 77% by mass. Now we will perform a simple experiment which shows that the volume of oxygen comes out to be 21%, or simply we can say with the help of this experiment we can see that if oxygen is present in the air, it is consumed, and how does what volume of this air it actually occupies. We will perform a simple experiment. So what we are doing today is, we are also performing a simple experiment. This is actually a petri dish, a dish in which this is a glass containing water, the colored water. What I am doing is, I am trying to pour water in this. It has been emptied out. I have taken a potato, place some matchsticks in it. तो थोड़ा एक्सपोजर पूरा रखना, मैं भी हूँ और ये भी दिखे. I'll place this in this, and then I'll try to light it out. Students, be careful while performing the experiment. So it can be seen that now what I will do is, I will try to invert it a bit. So you can clearly see that what has happened. The water which are present outside the water trough has been actually moved inside this glass. So why? Because during the process of the combustion, the oxygen present in the atmosphere, that is the inner atmosphere, is been consumed, and a vacuum is created, and from outside the atmospheric pressure pushes the water in the region inside having less pressure, and therefore you can clearly see there is a difference in the level. The water rises up to this particular height. So this is a simple experiment which is used to demonstrate how oxygen helps in combustion. It is used up, and by measuring this volume, it is possible to calculate what volume of oxygen. So the oxygen that is present is about 21% by volume, and nitrogen 79% by volume. Now, based on this only, molar mass of air, it comes out to be 28.92. Now, how does it comes out? We know that maximum is contributed by oxygen and nitrogen. Oxygen itself is 23% by mass, and nitrogen, it is about 77% by mass. So if you are considering 1 centimeter cube of this or particular thing, then actually what is done is, for 100 the oxygen, the molecular weight comes out to be 32 into 0.23, plus nitrogen, it is 28 into 0.77. This sum actually is utilized. Why? Because 23% by mass and 77% by mass of oxygen and nitrogen are actually present, and therefore this is the way how to calculate the molar mass. Now in question, in numericals, while solving the process of the combustion, what is actually given is that you are given with the composition of coal. Say it has carbon, hydrogen, nitrogen, oxygen, and it also produces ash. Two important things are to be taken care. Nitrogen and ash do not consume oxygen. That is, if you are given a sample of coal, sample of fuel, and the percentage composition is given in this manner, then for determining what amount of oxygen is needed to burn this sample, what is done here is the nitrogen and ash percentage, that is the ash which is left over, is not considered for calculating the percentage of oxygen. So only percentage of carbon, percentage of hydrogen and percentage of oxygen is calculated. Now see, you are supplying the air. The incoming air has oxygen in it, and you are having a fuel which also has percentage of oxygen in it. So the required oxygen for combustion is equal to the oxygen supplied minus oxygen available in fuel itself. The fuel itself has oxygen. It will be helpful in the process of the combustion, thereby decreasing the amount of oxygen required to be supplied from external source. So the oxygen, that is the required oxygen for the process of combustion, will be oxygen supplied minus oxygen available. Combustion, oxygen supplied minus oxygen available fuel. So in this manner it is actually calculated. Now see, how is it calculated? Suppose you have 1 kg of coal which contains only carbon. We have assumed that there is 1 kg of coal and it contains only carbon. Calculate what volume of air is required for its complete combustion. For solving any such kind of question, first of all, you should have a theoretical relationship. You should have a relationship between a standard relationship. We know that carbon combines with oxygen to give carbon dioxide. So, therefore, 12 grams of carbon combines with 32 grams of oxygen to give 44 grams of carbon dioxide, the known stoichiometric relationship. It means that if carbon present is 12 grams, then you are having 1 kg of coal and it contains only carbon. Therefore, 1 gram of carbon will require 32 upon 12 gram of oxygen by mass. Remember, it is by mass. So 32 by 12 grams of oxygen by mass is calculated. So what is done now is you are considering 1 kg of coal. So 1000 grams of carbon will be 32 by 12 into 1000 grams of oxygen by mass. So this much mass of oxygen is required. Say suppose this value comes out to be x grams. We know that oxygen is 23% by mass of air. Okay, so what can you do now is oxygen is 23% by mass of air. So 23% mass of air must be x grams. You can say why. So the mass of air is equal to x into 100 by 23. Now once you this is one manner. Second thing is that if you are obtaining this x gram, you can calculate it into volume of oxygen, as 1 mole occupies 22.4 liters at HTP. Now see, the most important thing is that 1 mole of a gas occupies 22.4 liters at STP. Had it been not given at a normal temperature and pressure, then you have to use the relation P1 V1 by T1 is equal to P2 V2 by T2 so as to convert, so as to obtain that particular relation. So 1 mole 20. So calculate the number of moles. So x gram number of moles will be x by 32 moles of oxygen, and depending on 22.4 liters, so you can calculate the volume of oxygen, and that depending on the volume of air, it will be whatever volume is calculated, say VML into 100 by 21. This is the manner how you actually using these kind of relationship, this kind of stoichiometric relationship, you actually calculate the process of combustion, the process of any kind of such. This was a simple example when you have taken only coal. When individual different gases are given, then actually we can calculate different things. Let us consider some other examples. I will just write the question and then we will try to solve it. Okay. 0.26 gram coal sample on combustion give 0.039 grams of water, 0.245 grams of carbon dioxide. Calculate the percentage carbon and percentage hydrogen in it. Now this is a different type of question in which you can see that 0.26 gram, so weight of coal sample 0.26 grams. Clear? Now on combustion gives 0.039 grams of water. So first of all, water. How water is formed? The water is formed by the equation hydrogen plus half O2 gives H2O. So if 18 grams water is formed, it corresponds to 2 grams of hydrogen. So you can see that if 18 grams water is formed, then hydrogen will be 2 grams of hydrogen. So if 9 grams of water is formed, it gives you 2 upon 18 1 grams of hydrogen. So 9 gram of water corresponds to 18 grams equal to this. So what divide by 2. So 9 grams of water corresponds to 1 gram of hydrogen. So weight of hydrogen water that was obtained is 0.039 grams. Now the main thing is that 0.26 grams of the cold sample combustion gave this. So what is 1 gram of water? Had it been, then it should be 1 by 9 grams of hydrogen. Therefore, if it is 0.039 grams of water, then it will be 1.9 into 0.039 grams of hydrogen. Say it comes out to be A grams when we will solve it. So percentage of hydrogen will be the weight of the hydrogen upon weight of the cold sample, 0.26 into 100%. Similarly, we can calculate the percentage of carbon from this much amount of carbon dioxide formed. See, C plus O2 gives CO2. So you can see that 44 grams of carbon dioxide corresponds to 12 grams of carbon. So writing it in a reverse manner, 44 gram carbon dioxide is equivalent to 12 grams of carbon. So 1 gram of carbon dioxide is equivalent to 12 by 44 grams of carbon, and carbon dioxide obtained is 0.245 grams of CO2. It will be 12 by 44 into 0.245 grams of carbon, and therefore percentage of carbon in the fuel, that is 0.26, will be 12 by 44 into 0.245 upon 0.26%. So this is the manner how to calculate percentage of carbon and hydrogen in the given sample of the fuel. We'll do another question related to combustion of the fuel. Now the question is, calculate the volume of air required for complete combustion of 1 meter cube of gaseous fuel containing methane 8%, hydrogen 40%, acetylene 2%, nitrogen 2.0%, and remaining ash. So again we have a question. We want to calculate volume of air. So what we are trying to do is, for calculating the volume of air, we will calculate volume of oxygen, and the gaseous fuel given volume is 1 meter cube for complete combustion. So if methane is 8%, then the amount or the volume of component in 1 meter cube. So 8, that is 1 into 8%. So it is 0.08 meter cube, 0.4 meter cube, 0.02 meter cube, and then it is 0.02 meter cube, etc. For calculating, see, for calculating the process of combustion, we will not consider the value of nitrogen and ash. So the combustion equation we will write methane. Methane combines with oxygen to give CO2 plus 2H2O. Hydrogen combines with oxygen to give H2O. Acetylene C2H2 combines with oxygen to give 2CO2 plus. Now if we need to balance the equation, then actually we can balance it as carbon, that is the molecule as we have used in the previous equation, CX, that was CXHY plus so you can balance the equation that 2 plus 2 by 4, that is 3 by 2 O2. So it comes out to be 3, that is CXHY plus molecule of oxygen gives CO2 plus water. We have been using the equation. For example, it was giving, for example, when you are using this, it was consuming this molecule, and when we were using hydrogen, then H2 plus half O2 gives H2O. So what we are trying to do is, for one atom, it was 1 by 4 of H2. So it actually, you are dividing it by this one. So by using this particular equation, when you are considering for one atom, then for one atom equation they can. So you can see that you can actually obtain a relationship for this kind of equation also, where you can easily balance the equation, that is the two atoms of the carbon and the hydrogen and then oxygen. Here you can see that oxygen 4, and if you consider the one molecule, then it can be written as 5 by 2. So that comes out to be, if we try to write it like this also, then you can see that 5 atoms of this one is there, and the hydrogen atom H2, so you can balance, that is X plus Y by 4, so it gives you the same equation. That is actually, so in this manner you can calculate. Now what is to be done is, while solving this is actually the equation. So you want to calculate the volume of oxygen. So volume of oxygen, you can see that for one volume we are using one volume of this oxygen. So for 0.08 it will be coming out to be 0.808 meter cube oxygen required. And for hydrogen, you can see that hydrogen combines with half of the oxygen molecule. So if it is 0.4, it is 0.2 meter cube. And for acetylene, you can see that the volume of the component is 0.02. So for 0.02 it is 5 by 2. So it comes out to be 0.02 into 5 by 2 meter cube. So you can add, and suppose on adding you get Z meter cube of the particular component. So the Z meter cube of oxygen is obtained. Now what is to be done? You have got the volume of oxygen, and therefore volume of air will be equal to this Z into 100 upon 21% by mass. So this much meter cube of air will be required. So this is the manner you just solve out the equation, the individual equation, and then based on that calculate the oxygen required. If in the fuel oxygen was given somewhere in between, then that oxygen has to be subtracted from this oxygen required, so that is available oxygen. So the net oxygen required will be the difference of these things. So actually with these sort of questions we can actually calculate the value of combustion of, or we can calculate the value of the combustion, and actually speaking, we can actually calculate what volume of the oxygen is actually required for this purpose. So finally what is to be done is that we have actually summarized the manner in which actually the calculation is to be carried out. Now, thank you very much for this kind of lecture that you have attended, and I hope you should have queries and any kind of problems that needs to be discussed, and you can surely send it to me through WhatsApp, or you can even mail this, so that we can have an interaction with you also, and finally the purpose is actually solved. Now, thank you for this. Thanks.